Introducing the graph of y equals the absolute value or the modulus of x. So let's consider constructing the graph of y equals the modulus of x just by first of all plotting some points. So we'll consider this table of values and have a look at, say for example, when x equals -5, y will equal the modulus of -5, which we know to be 5. And so we can plot that point. Similarly, when x is -4, y is going to be equal to the modulus of -4, which is 4, and we can plot that point, -4, 4. And we can continue when x is -3, y will be +3, plot the point. When x is -2, y will be +2, and plot that point. When x is -1, y will be +1, and plot that point. When x is 0, y is 0, the modulus of 0 is in fact 0. When x is 1, the modulus of 1 is 1, so we have the point 1, 1. When x is 2, the modulus of 2 is 2, so we have the point 2, 2, and etc. And we can continue plotting out points. And I'm sure you could agree that if we were to look at the decimal or fractional values between 0 and 1, 1 and 2, that we would get a linear pattern happening here. If we were to continue, the modulus of 6 is 6, the modulus of -6 is also 6, and the graph is going to continue in this fashion. And so we end up with a graph that looks like this. Y equals the modulus of x is this sort of interesting shape here. We have a key feature at this point here. In this case it's at 0, 0, and we call that point the cusp point of this graph, or the cusp of this graph. It's not a turning point, it's not a smooth turning point, it doesn't have zero gradient, so it's a cusp. It's where the two graphs meet sharply. The other thing we can observe here is that this is clearly a hybrid function, and we have two different graphs that are meeting at this cusp. So it's a hybrid function with two parts to it. If we think about the right hand side of it, this is obviously part of the graph of y equals x, the straight line y equals x, but we're only interested in y equals x in that first quadrant, so where x is greater than 0 or greater than or equal to 0. The other half of the graph is the line y equals -x, but we're not interested in the whole line y equals -x, we only want the part in the second quadrant there, so where x is less than 0. And so we get this hybrid function that defines the modulus function. It's the graph of y equals x, where x is greater than or equal to 0, and the graph of y equals -x, where x is less than 0. Now, just as a note, in the domain restrictions within the hybrid function, we could apply the greater than or the equal to part to either branch. It would be irrelevant, but it does need to be applied to one branch, and the convention would be to apply it to the positive subset of the domain. So we could have x is greater than 0 and x is less than or equal to 0, and it would still produce exactly the same hybrid function, but this would be the convention. So I just want to explore the algebra of defining the modulus function as a hybrid a little bit more, because this is really what's going on whenever we talk about the idea that the modulus or the absolute value signs make whatever's inside them positive. This is what's happening essentially. So if we were to think about letting x equal, let's say 5 for example, so if we were to substitute x equals 5 into the modulus function, we already know that when we take the modulus of 5 it's going to equal 5. But thinking about this hybrid function, okay, so we're substituting x equals 5, so x equals 5 is in this branch of the domain, so that means we have to put x equals 5 into this branch of the function. So we can see clearly that if we call this f of x, f of 5 is going to equal 5. Because it's going to go in the first branch of the function, x equals 5 substituted into x gives us 5. If we think about, for example, substituting x equals -2. So this time, -2 is in this branch of the function. It's in this part of the subset of the domain where x is less than 0. And so we're going to substitute x equals -2 into here. So if again we call this f of x, we know that f of -2 is going to be -2. And that's that where we're getting that making it positive, changing the sign by multiplying it by -1. And so f of -2 is equal to 2. And so you can see how this would work and mirror exactly what we've been working with the modulus function and the algebraic or the numeric definition of the modulus or the absolute value prior to now. And so now I just want to consider a slight variation. So if we were to now think about y equals the modulus of x minus 2, I want to think about this algebraically, generating the hybrid function, and then also we'll think about how that results in a graph and how that relates to transformations and things we already know about graphs. So if we're looking at y equals the modulus of x minus 2, we know that there's going to be two possibilities here. The thing inside the modulus signs could be positive, in which case it remains the same, or the thing inside the modulus functions could be negative, in which case we multiply it by -1. So we have two branches. We've got the situation where what's inside the modulus signs, that is x minus 2, is bigger than or equal to 0. And we know that if that's the case, what's inside the modulus signs is not going to change. So it will still be x minus 2. The other case is if what's inside the modulus signs is negative. So if x minus 2 results in a negative value, well then we know that we're going to need to make what's inside the modulus signs, we're going to need to reverse its sign, so we're going to need to multiply it by -1. And so this is the hybrid function. We can simplify this because we have x minus 2, so if we simplify the inequalities on the right hand side by adding 2 to both sides, so we'll have the graph of x minus 2 when x is greater than or equal to 2. And also we can see that because if x is greater than or equal to 2, x minus 2 will be a positive expression. And again, simplifying the bottom, so just expanding out these brackets, negative x plus 2, or you could also write that as 2 minus x, when x is less than 2. And again, that makes sense, because when x is less than 2, that makes x minus 2 a negative expression, and so we need to reverse the sign of it. So this is the hybrid function that results from the modulus of x minus 2. So now if we think about graphing this, so we're interested in the graph of y equals x minus 2, but only where x is bigger than or equal to 2, so only this much of it. And then we also want the graph of negative x plus 2, or 2 minus x, but we only want that graph where x is less than 2. And so here's the result of our graph of the modulus of x minus 2. We can also see how this is different from the graph of just the modulus of x. So here's the graph of y equals the modulus of x, the grey graph, and the blue graph is the graph of the modulus of x minus 2. And we can see that we've got a simple translation to the right by 2, which, given the work you've done with other functions relating to transformations, you would have expected that the modulus of x minus 2 would be a translation to the right by 2 of the original graph. But we can also see how that works algebraically and with the hybrid function definition.